Good afternoon and welcome to the workshop. In this video I'm going to tell you everything I've learned over the last couple of years about milling in the ML7. As you can see now, it's set up in turning mode. We have the cross slide and the compound slide with a cutting tool on it. And the first thing we need to do is get this off and set it up for milling. It's quite a sensible idea now to clear out the T-slots where the cross slide was, because this is where we're mounting the machine vise. What you can see here are the two kinds of vertical slide for the ML7. If I turn them round, the difference becomes a bit more apparent. This has two bolts which fit into the T-slot of the carriage, and there's only one axis of movement, which is directly up and down the x-axis in relation to the spindle nose, which would be here, or if you twist it 90 degrees, here. This is a compound vertical slide, which means if you can imagine the T-slot is underneath here, it means it can be rotated this way, and if this nut is loosened, it can be rotated that way. And then you can traverse the slide in that axis. So you could have something that was at 45 degrees this way and then 45 degrees that way for a really strange compound angle that you are milling or drilling in reference to the spindle. Of these two, the compound vertical slide is most highly regarded, but actually the fixed vertical slide provides a much more stable base. And generally, you don't need the fine adjustment of angles that the compound vertical slide provides. And in fact, you can use packing or blocks in here to offset the piece by the required angle without the need for this complex and fairly flexible arrangement that you have on the compound slide over here. It is entirely possible to use clamping, such as the C-clamps, directly into the T-slots of the vertical slide. You don't actually need a vise for a lot of the jobs that you might wish to do. And another reason for this, the versatility of these vertical slides, is that you have so many ways to fixture the work. You don't always need the vise like this. That said, a vise like this is the most common accessory found on the vertical slide. This is a 2-inch machine vise, and as you can see, it's got a fairly wide aperture. The primary function of this is to hold work, typically against the back or using parallels to offset it, and then clamping down this way. That obviously has the drawback of irregularly shaped work is clamped very inefficiently and weakly. You can't clamp circular surfaces if the radius of them is greater than the distance between the back and the front of the jaw. So using swan neck clamps and T-bolts is a very useful option if you can get away with it. This of course allows you to mill the full face of a part, whereas with the clamps you can only mill where the clamps aren't. Once we have identified the kind of vertical slide we're going to use, and we have slid it into the T-slots on our carriage, we now need to ensure it's aligned. The most straightforward way of doing this for any, not just this compound slide, is to wind it down so that the rear machine surface of this dovetail meets the machined surface of the carriage. And then you can, a bit further, you can push it backwards. So in any old angle like this, push it backwards, and then you can now be reasonably certain that the back of the vise i.e. this section in here is now parallel with the front of the cross slide. If you're milling for the first time, the chances are you might be using something like a 3-jaw chuck in the spindle to hold your milling cutter. And that's not terrible, but there is a small problem. If you're taking large cuts, then the hardened inside face of these jaws and the hardened shank of the milling cutter won't provide a really solid grip. So there's the chance that the milling cutter will catch and then spin in the jaws, which is not good for the jaws or for the milling cutter. So while that's possible, if you're very careful with light cuts, what's far more preferable is to use these Myford collets. Now, these fit in. This is what the collet looks like. Let's go around here. This is what the collet looks like. And this is a close your ring. This inside thread here matches the thread on the spindle. So the process is to insert the collet into the ring, insert the ring into the taper and start screwing it down. Insert this is a piece of steel, but this would be the milling cutter, and insert the milling cutter into the collet. Helps if you undo it first. Tighten that right up. And in this case, I've got the lathe already in back gear. Now, it's a terrible idea to whack the chuck if you want to unstick a chuck with it in back gear, but it's fairly okay for the kind of hand pressure for tightening this collet here. So now we know we've got a very strong grip on this collet onto the milling cutter that's here, and we've got lots of space and lots of air around us. And that's one of the biggest challenges on milling on the lathe, is that by the time you've wound in your vise and you're milling, there's a very limited view of the workpiece. You have to trust the dials, and there's very little visual feedback. So having a collet chuck, or a collet holder in this case, significantly increases the visibility of what you're doing. These collets come in all shapes and sizes. They were originally issued by Myford and have sizes from, I believe, 1/16 to 1/2 inch in 16th intervals. You can manufacture these, and there are drawings in the Model Engineer's Workshop magazine, I think, in fabricating your own collets, which is significantly cheaper, and you have intermediate sizes. So I have got 9/32 and 5/32, which you just saw on the lathe, which weren't initially issued by Myford, but are very handy in gripping odd size reamers and drills and workpieces. Right now we have a 1/4 inch 4-flute end mill inserted into a 1/4 inch Myford collet, tightened up nice. I've taken the lathe out of back gear, and if I take off the clutch just to make sure everything's okay, which it does appear to be, I can start the lathe. You can see that's what we're going to be milling with. To be absolutely clear, you want the lathe running in the fastest speed possible. There is no material and no depth of cut that will require anything lower than the fastest speed, unless you're milling stainless steel and you're using a cutter larger than, I think, 3/8 of an inch, which is quite an unusual combination. But if you were doing that, then you need to use one less. The rest of the time, the very fastest speed is probably too slow. And one of the challenges that we'll have is that the lathe can't turn fast enough for smaller mills. So you might have a 1/16 or a 1/8 end mill, but that requires a speed far in excess that the ML7 can provide. And that's bad because it means the chips don't get cleared fast enough. The end mill will rub rather than cut, and it will get blunt and you'll break it. And I know this because I've already broken a couple. So stick with a 1/4 inch end mill or larger, depending on what you can find. Generally, I find this is a happy medium between having to do so many passes and removing material adequately. One of the other big challenges in milling is how we're going to hold the part. These are machined faces, which are fully parallel with each other and hardened, so you can crank this down onto a piece of work and it should hold it very tight. However, if the work isn't perfectly square or is tapered in some way or round, you may find that the work is gripped very securely on one section but not on the other. And the easiest way to resolve this is to use a tiny bit of packing. So let's just say, for the sake of argument, we're going to mill the side of this clamp. Put this in here like so, and then use a piece of wire, brass or copper wire, something softer than the material you're trying to mill. And then what that will do is push this piece hard up against the back, and it'll be totally flat with the fixed jaw. The top jaw, if it needs to move or rock, if the part needs to isn't perfectly flat on top, this will take up the slack. So you can clamp that down really tight now and know that this piece is very secure against the fixed jaw. The second major challenge with using the machine vise is if the workpiece is too small. And in this case, let's just say we're going to mill the face of this piece of brass off. It sits behind the jaws. And there's no real way for us to be able to bring this forward without something like these. These are parallels. These are small parallels. I got a set, I think, for £20, and it was 3 or 4 pairs in 1/8 inch increments. This is a 1/2 inch and this is 5/8. You can insert this into the vise and you can then place your work against the parallel and then clamp it down like so. When milling on the lathe, you have 3 axes that you can control, in theory, simultaneously. You have your Z-axis this way, you have your X-axis this way, and your Y-axis this way, I believe. That means that you can plunge, you can traverse either horizontally or vertically. You really don't want to try to do more than one at the same time. And what that means is it's a good idea to lock as much as possible and use only one direction for traverse. As a side note, this lead screw hand wheel has been invaluable in milling operations. There is a pointer here and a wheel with 125 divisions of 1 thou each, which means 2 turns moves the carriage a 1/4 inch, for example, or 4 turns will give you 1/2 inch. What you can do is you can engage the feed screw on the carriage down that way. You can wind yourself in 10 thou, lock the carriage, take a cut, and you can keep doing that, and you know that you're only ever taking cuts of say 10 or 15 thou. The last aspect and the most tricky is the direction of cut and the direction of traverse, and they must always be opposite. That's called conventional milling and what we do all the time. For example, if we were cutting a shoulder into the top of this part, the cutter would be rotating towards me in traditional fashion. I need to pull the part towards me in order to cut effectively. If I do it in the other direction, there will be a lot of vibration and a lot of chattering. It's possible, but it's not ideal. That's the first rule. The second rule, which is equally important, is that you can't cut in such a way that the force of the cut is upwards. So I couldn't, even though I would be technically correct, if I was milling the front face of this part, I would be traversing downwards against the back of the cutter. What's that going to do, however, is the cutting forces are pushing upwards, and as you can see, the backlash in the vertical slide exists. the carriage is not designed, sorry, let me zoom out. There's backlash in the vertical slide, and the carriage is not designed to be resistant to upward forces. It's very resilient downwards, which is why you can cut, if you're cutting on the lathe, your tool is normally here, and the workpiece is pushing down on the tool, and the carriage and the cross slide resists it. But in the other direction, the forces are pushing it upwards, and it doesn't know what to do with that. So don't do that. That said, let's get milling. I hope that short video was useful for you if you're either milling in the ML7 or you're thinking about doing so. I can highly recommend the book Milling in the Lathe from the Workshop Practice series. It's only a few pounds. It will give you lots of charts and diagrams on things like depth of cut, speed of cutting, and so on that I didn't go over here. Hopefully though, I've given you a good basis to get started. If you're interested in this kind of content, please do consider subscribing to my channel. I do a lot of this kind of thing, building stationary engines, hopefully building locomotives soon, and I'd love to see you there. So thanks for watching.